Very welcome to our next session. And our today's speaker is Caiyun from our department and our Stochastic research group. And she will talk about books and packing dimensions of orthogonal projections, nice homogeneous Gatzouras-Lalley cartons. Please.
Thank you for your introduction, and thank you for this opportunity. Thank you for giving me a chance to give a talk about books and packing dimension of orthogonal projection of special self-contained sets, that is homogeneous Gatzouras-Lalley capit. And we begin from.
Click on the screen.
From classical question. So if we fix angle theta and let p theta denote the orthogonal projection onto a plane, and if we given a Fourier set, a general set, and is it true that the dimension of the projection set is equal to a minimum original dimension and 1, and for almost every direction theta? And here, a dimension could be box dimension, Hausdorff dimension, packing dimension, or some other dimensions. And there is, this question is one of the central questions in geometric measure theory. And there is a classical answer given by Max Trent in 1954. And in 1978, Kaufman extended, in fact, not extend his result, but he used a capacity method to reprove the original result in 2 dimensions. And later in 75, and Martina just extended the result to higher dimension and also used Kaufman's capacity method. So the reality is that for Hausdorff dimension, if a set it is a Fourier set in Rn space, and Hausdorff dimension it is strictly greater than k, where k it is greater than n, since we consider projection to a k-dimensional subspace V. And then projection set has positive k-dimensional Lebesgue measure. And if the original set has Hausdorff dimension less than k, then projection preserves Hausdorff dimension. So the result for Hausdorff projection zero, it is complete and it is very clean. But what about projection of both dimension of the projection set and the packing dimension? So for that case, the situation is much more complicated. Well, for the simplest case, that if the set has same Hausdorff dimension and the box dimension, then as a direct corollary, here the box dimension of a projection set which is equal to minimum k and the box dimension. Well, it is trivial because a lower box dimension it is greater than your Hausdorff dimension. So lower box projection set it is greater than Hausdorff dimension, and since it is a projection, it is Lipschitz. So it is less than original box dimension, and then it is equal to Hausdorff dimension. So we get the equation. It's trivial. But for general sets, in 1994, Jalapa gave an concrete example that there is a Fourier set E such that the upper box dimension of projection set, it is strictly less than minimum k space, projection space, and upper box dimension of original set, and similar for packing dimension. So this gives upper bound. And in 1996, Fractal and Horowitz, they gave a lower bound for almost every direction. Packing dimension has such lower bound, and this inequality is sharp. But there is no inequality. So we get upper bound and lower bound, and we don't know if they are same value, and so it is quite difficult to, it is unknown about the exact value until in 1997, Orthogonal and Horowitz, they just define a new concept that is dimension profile, and this value I didn't write the exact definition in their paper because it's too complicated, and we just need to know that. So for every direction, for every k-dimensional subspace, the projection set has packing dimension. It is less than a value called called packing dimension profile of set E. And here the K it is projected to k-dimensional subspace. If V it is an angle theta, then that is 1, K it is 1. And a similar result for upper and lower box dimension result. And moreover, this is not only an upper bound, but also inequality hold for almost all k-dimensional subspace. So this means that, in fact, they have solved problem about projections, box dimension, and packing dimension. They have solved this problem. However, the definition of a dimension profile in their papers are indirect, and it's very hard to work with. We don't know what the exact value is. So we don't know. We cannot compare this value with minimum, the original box dimension, and the space, the dimension k, the space of a dimension. The dimension of a space k. So we don't know. We cannot compare and actually write it here. So this value, it is equal to, I don't know if it is equal to minimum k and the original side, box dimension of the original side. So this is the question. Well, fortunately, in 2021, Faulkner he provided a new capacity approach to redefine the box dimension profile. That is, given a Borel set E or that is a set or general set, and let k strictly less than n. So since we need to consider projection onto a k-dimensional subspace, and given a value r greater than 0, and we define 1 over c KRE, that is r appears here, and k it is if we project to k-dimensional, then it will power k. And the infimum of mu over mu, it is a probability, a real probability measure supported on the closure of set E. And he showed that for any Borel set E, this is called lower box dimension profile that is introduced in this page. So here I didn't give the exact definition, but in 2021, Faulkner proved this value, the original definition, it can be equivalent to be written as this limit in log CRE divided by negative log R. And then based on this, we can write as if E it is a real subset of Rn, then for almost every k-dimensional subspace, the lower box dimension of PVE it is equal to a right-hand side. And the right-hand side, I think we need to keep it in mind that the right-hand side it is dimension profile, lower box dimension profile. Here, this is upper box dimension profile. This value. And so, since we have such form, it is possible to compute now. But in fact, before us, no one exactly computed. Okay, so what are the exact value of? Here, I just use the lower box dimension. In fact, we only need to compute the box dimension profile. We only need to compute the right-hand side, right? And the right-hand side, it is constant, independent of the direction V, or subspace V. Well, in fact, Borel, Faulkner, and Frieder, they give some partial results. So in 2021, they give such assumption if E which is bounded set such as lower intermediate dimension of E, which is continuous at 0, then they prove that the Hausdorff dimension, well, lower box dimension of PVE, which is K, if and only if, well, almost everywhere, if and only if the Hausdorff dimension, which is greater or equal to K. So the Hausdorff dimension greater or equal to K, it will determine that the lower box dimension projection size, which is K. It looks like a little bit strange, since it's natural to think that maybe it is box dimension of a set is greater than K. Then we have a lower box dimension. They are connected, but in fact it's not. Well, so what kind of set satisfies this condition that lower intermediate dimension is continuous at 0? So can we have some example that satisfies this condition? Yes. Well, in fact, in 2019, when they first introduced the definition of intermediate dimension, they mentioned that they proved that if E, which is a Bedford-McMullen cabinet, then intermediate dimension, it is continuous at C. So as combining these two papers as a direct corollary, we have if E, which is a Bedford-McMullen cabinet, as an application of intermediate dimension result, we have if Hausdorff dimension is greater than 1, then the box dimension of a projection set exists almost everywhere and it is equal to 1. So here V is theta and K is 1. And if the Hausdorff dimension is strictly less than 1, from their results, we only get the upper box dimension of a projection set is strictly less than 1. But there are some questions. So does the upper box dimension and lower box dimension equal or the exact value of our upper box dimension almost everywhere? Since it is a constant, we know that it is a constant, and that constant it is dimension property, as I emphasized several times, and I want to emphasize it again. So the lower box dimension of the projection set, which is almost a constant, so almost everywhere it is constant. And this constant, it is called as dimension profile. Okay, and then, in fact, we know that there are some problems we cannot solve. And they mentioned in their article, I just copied a sentence from their article, and they said, this surprising application of the intermediate dimension results seems difficult to derive directly. So in fact, they don't know how to get a box dimension with the projection set from a Hausdorff dimension which is greater than 1. They only know that from the application of intermediate dimension. And there is very little known about the box dimensions of projections of Bedford-McMullen cabinet. Well, in fact, Bedford-McMullen cabinet is the simplest self-ordained set, but they don't know the projection results anyway. And now, aside from them being almost surely constant, yes, we emphasize many times that that constant, it is box dimension profile. So, what are the exact values of the upper box dimension of projection set and lower box dimension in each of the following cases? So the first case that Hausdorff dimension, it is, well, here we consider a Bedford-McMullen set. E, it is Bedford-McMullen set. And if Hausdorff dimension, it is strictly greater than 1, they have solved the problem, part of the problem. Because if it is greater than 1, then the box dimension of a projection set, yes, they have solved this it is 1 for almost everywhere. But what if the Hausdorff dimension it is strictly less than 1, but the box dimension is greater than 1? Or the box dimension is strictly less than 1, strictly greater than Hausdorff dimension. And we have some conjecture. So for example, for this case, is it possible that a projection of a box dimension, a box dimension of a projection, not here. So is it possible that a box dimension profile? So for example, I write it here, E. It is strictly greater than Hausdorff dimension of E, but strictly less than 1. And for the third case, it is possible that the box dimension profile it is equal to the original box dimension of set E, or maybe it is strictly greater than Hausdorff dimension of E, but here it is strictly less than box dimension, or maybe we also have it is equal to Hausdorff dimension. So there are many conjectures, and in fact, before us, and it seems that no one has solved such problem. And one more question. Okay, sorry.
Here is the adaptation because it will be kept from the other slides too.
On other slides. Okay, yes, I will. Okay. And so do we have the upper box dimension it is equal to lower box dimension of the projection side? So these are many questions. And in fact, we solve all problems. And as they start that the spring application seems difficult to derive directly. Well, in fact, we derive it directly, and it is really difficult. Yeah. So next, I'd like to state our result. So we determine the box dimension profiles of homogeneous Gatzouras-Lalley cabinets. In particular, the backbone McMullen cabinet, it is a special case of such GF cabinet. And the box dimension profile, as I mentioned several times, that in fact it is a constant, and that constant, it is the box dimension of a projection set almost every direction. So let's first recall some definition background. So let X be a compact set, and we call a family of uniform contracting maps as an iterated function system. And in 1981, Hutchinson proved that there exists a unique non-encoded compact set K, such as K is the union of these pieces SIK. And if Si are similarities, we call K as a self-similar set. And if Si are affine maps, then K is called self-affine set. So from a collection of contracting maps, how to get an attractor, that K is an attractor, how to get. So for example, if we have a unit ball, and then there are two maps, F1 and F2, and it is contracting maps. They are contracting maps, and it maps the ball to ellipse, and we iterate infinitely many times, and then your intersection set, that is attractor, and that is self-affine set. And our object, that homogeneous Gatzouras-Lalley cabinet, in fact, it is a special self-affine set. So it is generated by such IFIs, phi ij. So I'd like to describe this IFIs by this graph. So here, this is the unit cube, and then with phi ij maps the unit cube to rectangulars, And so to many rectangulars, and they are in many columns. And for the first column, there are 1, 2 until L1 many rectangulars. And for second, it's 1 to L2. And then we assume that the width of this column it is greater than the height B. The rectangles they have the same size. And these two conditions are separation conditions. So that the rectangulars in the same column, the interior of the rectangulars are disjoint. And for the rectangulars in different columns, this assumption ensures that the interior of those rectangles are disjoint. And then we iterate infinitely many times, we get a self-contained set, and this self-contained set is called homogeneous. Gatzouras-Lalley cavity. Why it is called homogeneous? Because every rectangular has the same size, so it is AB. And then we want to consider the box dimension of the projection set, projection of the homogeneous Gatzouras-Lalley cavity. That is appeared in our title. Okay, and then we notice that Bedford-McMullen cavities are a special type of homogeneous Gatzouras cavities. So here it is AB, and it can be irrational, but here it is Bedford-McMullen size. It is 1 over M, 1 over N, and it's clear that it is special case. So our result will cover Faulkner and Friedler their result. So before we consider the projection, the box dimension of projection set, let's first compute its original set is Hausdorff dimension and box dimension. So here, the dimension formula was given by Gatzouras-Lalley in 1992. And we notice that here L it is defined as the sum of Li, that is how many rectangulars totally we have, and lambda it is the ratio log B divided by log A, and we see phi ij has uniform fibers if L1 equal to L2, so this means that every column they have the same number of rectangulars. So that is uniform fiber. And we notice that the Hausdorff dimension of E, which is equal to box dimension if and only if E has uniform fibers. And here, notice that if L1 is equal to L2 to Lm, then Li can be written as L divided by M, and then it means that it will imply that the Hausdorff dimension is equal to the box dimension. So it is direct result. And we found this result where we refer to Carly and Barney and Slomia's book. We just use this result. And the Hausdorff dimension it is 1 if and only if. A since it is 1 if and only if the numerator it is equal to the denominator. So A is equal to this value. And let's see a concrete example. So if EA, it is a homogeneous Gatzouras-Lalley cavity generated by 3 maps. And these 3 maps here, and one in corner, only in corner, and we compute based on their formula. So here, the formula is here. Since there are only 2 columns, M is 2. And the first column, there are 2 rectangulars. So L1 is 2, L2 is 1. And then we can compute the Hausdorff dimension and the box dimension directly. And we know that the Hausdorff dimension is equal to 1 if and only if A takes this value. The numerator is equal to denominator. And then we consider 3 cases. So our first case is that for Hausdorff dimension, it is less than box dimension, less than 1. Since we know, based on this formula, we know if A it is less than this value, Hausdorff dimension it is less than 1. So And if A it is less than 6 to the power negative 1/2, then it is less than 1. So the first case is very small, Hausdorff dimension less than this. And for the second case, we still have Hausdorff dimension less than box dimension less than 1. But for the third case, Hausdorff dimension is less than 1, but box dimension is strictly greater than 1. However, since A here it is very small, and if we consider a projection, orthogonal projection, since it's very thin and it is possible to think that, it is natural to think that maybe a projection site has the same box dimension as the original site. And for this case, maybe the situation is different. Since it is bigger, but if we project it to a lane, then it becomes shorter, quite shorter. And maybe the box dimension of the projection site is strictly less than box dimension almost everywhere. And for a third case, the Hausdorff dimension less than 1 and strictly less than box dimension, it is we may guess that maybe the projection site has box dimension 1, but we don't know what if it is 1 or less than 1. And now let's see the result for the projection site for this projection site here. The mean result shown in the next section will imply that, in fact, we find another critical point A1. And if A it is almost equal to 0.3968, if A it is less than this value, then here one box dimension profile that is the constant that box dimension of the projection site, it is equal to this value almost everywhere. So it is equal to the box dimension of EA. So this implies that the orthogonal projection preserves the box dimension. And if A it is greater than this critical point, but it is less than this point. So this point, as we said before, this point is where the Hausdorff dimension it is equal to 1. So this means that if A it is less than this value, that is the Hausdorff dimension it is less than 1, then we have a projection site has box dimension strictly greater than Hausdorff dimension and strictly less than minimum box dimension and 1. So for the third case, if A it is greater than this value, that is the Hausdorff dimension of E it is greater or equal to 1, then a projection site has box dimension 1. And based on Falconer's result, in fact, Falconer's result imply that if C it is greater than this, then the Hausdorff dimension greater than 1, the projection site has the box dimension 1. And their results also have partial result of B. That is, if the Hausdorff dimension it is less than 1, then the upper box dimension of projection site is strictly less than this. But they didn't know that, in fact, there is another critical point that if A it is less than this, we have this equation. So we consider all cases. And so before I state dimension formula, let's recall the setting. So let E be a GL capital generated by phi ij based on that graph I drew before, and we assume that EA does not have uniform fibers, because if it does, then the Hausdorff dimension of the site is equal to the box dimension of the site. So a projection theory, we can just apply a mass chain projection theory about Hausdorff dimension. Then we are done. It's trivial. So and next we fix lambda lambda, it is a ratio of small rectangular, and log b divided by log a. And m, which is columns, how many columns we have, and L1, Lm. Okay, I'd like to refer to the graph we had before. Yes, here, that is we fix lambda, that is log b divided by log a, it is lambda, we fix ratio. And then we fix L1, we fix m, that is we have m columns. Well, we can transfer and then translate, and then we fix Li, that is each column, how many rectangles we have are fixed. But we can just move it, but to make sure that the interior of the rectangles are disjoint. So that is, and for example here, we fix the first cardinality of rectangles in every column, and but A changes. And then we view A as a parameter. And we define two critical points. Infinity we defined before. And the infinity comes from the result of Hausdorff dimension. That if A it is infinity, then Hausdorff dimension is 1. And A star, it is the value such as rectangles in the unit cube. Because here MA, that is we have M columns, and otherwise it is A. So MA it is less than 1. And the next one, A to the power lambda, in fact it is B, since lambda is log B divided by log. So, and how many rectangles in every column? Biggest one it is maximum Li. So since the rectangles should be in unit cube, so maximum Li times B, it is less than 1. So it is very natural to define such value is that. And then what is the result? Based on, besides these two critical points, infinity, we also define A0 as 0. And we prove that we can find a strictly increasing sequence, A1, A2, and with AK converges to AK infinity. And then for every k, we define functions f k on this interval. Since we have a sequence of increasing sequence, then we get many small intervals. And if we consider interval ak and infinity, we define function f a. I will give a precise definition of f k later. Since here we just need to know we have a sequence of functions, and f function it is pointwise. It is pointwise function. If a in this small interval ak, let's turn here. Yes. And so we have a sequence A0, A1, and AK, well, infinity, and A star. So on each interval, we can define, so Fk, it is defined on Ak to infinity. So A1 to infinity, A2 to infinity. But Fa, it is defined if we only consider A in Ak to Ak plus 1. So here, that is F1A. If we consider Fa is defined if A in A0 to A1, that is F1, and then A1 to A2, okay, that is A2. And then we define a sequence of functions and we define Fa. And if A is greater than infinity, less than A star, then Fa is defined as 1. So this is a function, and what is our result? Okay, for every A between 0 and less than between 0 and A star, we have a box dimension profile of EA. It is equal to FA. So we just give a precise expression of the box dimension profile. So it also implies that the lower box dimension of projection set is equal to the upper box dimension of a projection set almost everywhere. Since this value, in fact, this value it is box dimension of projection set almost everywhere. Since projection it is a constant, and this is a constant almost everywhere. And what is FA? And what is the property of FA? And based on this, can we compare the Hausdorff dimension of EA and the box dimension of EA with this value? This is which is interesting. So first,
sorry, can you just go back and remind me about the difference between A infinity and A star? Okay. A infinity is where the Hausdorff dimension is equal to 1.
Yes, and A star is largest A such that all rectangulars is still inside the unit group. Since M, it is how many columns we have, and so I'd like to go back to this graph.
Yeah, and is it clear that A star is bigger than A infinity?
Yes. I will explain it later, and I'd like to see that since there are many columns and the length it is A, so MA should less than or equal to 1. And the height, since the height it is B for every rectangular, and maximum Li times B should less than A. So that is why we have A star. And I'd like to see that A infinity it is strictly less than A star. So from their definition, we see that here. Yes, A is not a long proof, and we can try here. So maximum, and this implies that this is A lambda. This implies that A star lambda, it is less than minimum Li -1, right? So A lambda times maximum less than 1, so it is minimum Li inverse. And we erase lambda, and so it is 1 over lambda divided by lambda. So A star, in fact, if it is maximum, then it is equal to, right? And so we consider different cases. So first, we assume it is a teen's maximum, and this value. And here, notice that it is a sum Li inverse. So it is less than, we only pick one. We only pick one, and we pick which one. Maybe since here negative, so we can replace it maximum and slope, and then 1 over lambda. So we pick a maximum one, so it is less than this value. It is quite clear. Is it clear? Yeah. And then for this case, so A, if we consider A star, it is 1 over M, and we want to prove A star it is greater than infinity. Then we just need to consider where you apply the Jensen inequality. Since the right hand side it is the sum Li 1 over lambda to the power -1. So if we multiply this sum and then 1 over M, the sum Li 1 over lambda, where we apply Jensen inequality, since x to the power 1 over lambda, it is concave function because lambda is greater than 1. So we get it is greater than the sum 1 over M Li and to the power 1 over lambda. And the sum, it is the sum of Li, it is how many rectangulars we have, and divided by M. M is how many columns we have. And in fact, we have, since it does not have uniform fibers, it implies that, so if there are two Then if this is 1, for this column there is only one rectangular, this is 1, it's not satisfies this assumption. So we need to add one more because it does not have a uniform fiber. This implies that the total number of rectangulars, it is strictly greater than the total column we have. So L is strictly less than M, and the sum Li divided by M, it is greater than 1, so it is strictly greater than 1. So we prove this one. So yeah, this is observation. Okay, is it okay? Yes, okay. Thank you. And then we get, so maybe someone already forgot what it is. Maybe let's turn to the first 3 or 4 pages to recall the dimension profile. Here, yes, here. That is the dimension profile. And that is one box dimension profile, lower box dimension profile, it is CR1. That is, we project onto a k-dimensional space. And if we, since here we consider self-open set on a plane, so we consider to project onto a lane. So k, it is 1. And lower box dimension of a projection set, it is equal to this value, k-dimension box dimension profile. So this value for almost every k-dimensional space. So this value is almost a constant almost everywhere. And if we compute this value, then we get the result for the projection set. And then let's go back to the statement. Yes, and first we get the dimension formula here, and we'd like to compare this projection box dimension of projection set with original box dimension and the Hausdorff dimension. And the first result is that it is equal to the box dimension if and only if A it is less than 1, greater than 0. And second one, it is 1 if and only if the Hausdorff dimension it is greater than 1. So this first part was the first part for this direction. Were proved by Faulkner and Frieda before, but in fact they don't know if this is true. Yeah, so now we finish this part, and okay, and then if A it is between A1, since we have 3 critical points, A1, infinity, and x star. Well, which are important. So A1 and infinity are important. If it is less than A1, then the projection set has Hausdorff dimension as the original set. And if A it is greater than infinity, then it is 1. But if A between A1 and infinity, then your projection set has both dimensions strictly greater than Hausdorff and strictly less than minimum. So the mass train type projection zero does not hold for box dimension. And what's the property about function f? Well, f it is strictly increasing and it is in one uninterval. And recall what is f, and I'd like to draw a picture here. And this is A1, A2, A1, A2. And AK plus 1, and we have many. This is F1, and this is F2, and then we continue. So it is a piecewise function, this is F1, and totally it is F. And F it is C1 on the interval, and it is real analytic on each AK to AK plus 1 on this interval. This means that the function fk, so this function fk, it is analytic on an open interval AK to AK plus 1. However, F, it is not twice differentiable at a point AK. So that is point AK from where we choose different functions. And that is why we call it F. It has infinitely many how to say phase transition. That is why it appears in our title. And it has many second order, and it is called second order phase transition, since it is not twice differentiable, but it is one. And so that is the main result. And maybe we can take a look. And one more question. So what are the sequence AK and the function FK? Since I said that we have created points AK and we construct a sequence of function FK. So what are the sequence AK and FK? Let's give a definition here. Let's GT as the weighted average of log Li. So if we denote Qt as a probability vector, that it is Li to the power t and Lj to the power t, and j from 1 to m, since we have m columns, and I from 1 to m. So this is a probability vector. And then we consider the weighted average of log Li. And for HT, in fact, it is a big HT, that is the entropy of the vector HQT. Okay. And then we define, now we are ready to define a function TAX. TAX is defined as G inverse. Well, it is, we write it whenever it makes sense, since it is the inverse function of G, and we need to consider range of G. And then AK, it is the unit value, satisfies AK iterate K times. If we pick A as AK, and we need to find a proper A, such as if we iterate K times, then it is equal to at 0, then it is equal to 1. So that is how we find AK. And the sequence AK is strictly included. I'd like to give you a rough graph. And so here, that is TA1, 0 should equal to 1. Then we pick that is A1. And TAK, that is TAK iterate K times is 1. And then this is TA1, so it reaches 1 here. And for A infinity, it is a blue curve. And if A between A1 and A infinity, then the curve should be in this area. And for example, what is A4? A4 is that that is a curve, and if it is A4, it should satisfy that TA4 0, it is strictly less than 1. But we continue to do the integration, then it is TA4 2, and then we continue TA4 3. And the first time it reaches 1. So that is how we get A4. And Fk, it is defined as a function, since we have an entropy of a probability vector, and entropy of here we define HT. And so this T, it is TA iterate K times at 0. And then get such formula. Okay, I think 1 minute on that. So I do not have time. So I just give a rough idea of give a concrete example, and we compute what is F. And then we compare Hausdorff box and the projection of box dimension of projection side. This is purple one. So, and the blue, it is original box dimension, and green it is Hausdorff dimension. And if A less than A1, then blue and the purple curve coincide. And if A between A1 and infinity, then the three curves separate. And that's the result. And thank you, since I do not have my time to explain details. So, yeah. Thank you.
Thank you very much. Questions, comments?
Yeah, I have some questions about these numbers. So first of all, do I understand correctly that in general it's not easy to calculate them? And how about in the case when we have a bed for Blackman and carpet? Are the computations simpler then?
Yes, we have computer Gatzouras-Lalley carpet and backbone Macmillan carpet. It is special.
Yeah. I mean, but okay, but if you give a general carpet of the general type, then you have no exact formula, just equations.
Oh, we know the formula. In fact, at A it is the formula.
Yeah, but it's what do you mean formula? I mean, okay, yeah, but there's a solution to some equations and things like that.
Yes. This is the truth.
Yeah.
Yes.
Yeah. So, but will it be simpler in the backward case?
Well, in question, not really.
Not really.
Yeah.
Thank you.
So you have formulas for these numbers A, K.
Yes.
Can you extract any other geometric information from these? Like for A1, there's a specific meaning in your theorem. Do these other numbers A2, A3 have any other meaning?
Well, in fact, it is why we have such sequences based on a proof. That's why we get such creative points. Because if you want to estimate some value, we need to construct some measures, and we notice that if A in some intervals, then the construction of measure should be changed. And if A between that interval, then this measure with such probability vector is okay. But if, so for example here, it is A where A appears. And if A in different interval, we consider different probability vector, and then we construct different product measure, and then we can estimate. So that is why we need such AK, and the definition of since AK should satisfy CAK iterated K times is 1, and in fact it is we need this because we construct such probability vector. That's how we have such AK.
Is lambda bigger or smaller than 1?
Lambda is bigger than 1 because lambda it is log.
That is what in the ratio.
Yeah, ratio log B divided log A. Yes.
So if you go back to the last slide, the next slide, the previous one, yeah, okay, so look at that one. Not previous. Yeah, that one, yeah.
Sure.
Further questions? Online people? If not, then let's thank Caiyun again for this wonderful talk.